in terms of dispersion, and after that I'll gradually go on to various tests of significance, and there are different tests of significance used in statistics, and out of that I'll be focusing on two of them. One is student's t-test, another is on chi-square. These are the two important tests of significance which are of importance in your undergraduate level. So I'll be focusing on that. And before beginning with all this, just to brief you the importance of biostatistics in medicine. Many of you might have experienced by now that we use a lot of data, and data especially in relation to, say for example, anthropometric measurements, height, weight, and also other biological measurements. Like we take out different samples, blood samples, and try to measure different biochemical parameters like hemoglobin, then also lipid profile, the kidney profile test, then the kidney function test, the liver function test. There are different parameters I use. Now, if I ask you like the normal blood pressure level among the adults, the level is, let us say, it is 140, the cutoff limit is 140 by 80 millimeters of mercury. Now, why 140 and 80? Why not 138? Why not 130, the cutoff limit? And why not it is like 90? Why not it is 100 in the diastolic? So you can keep asking me different questions like this. Now, the cutoff has been set based on the normal distribution in the population. Please remember that for a population norm, we try to find out the population norm based on taking various samples, various readings from the population. In this example, I have told you about the blood pressure. So blood pressure is measured but for males, females in different age groups, starting if it is adults, so let's say above 18 years. And in the population, whatever the distribution is there, we try to find out from that. And we try to, again, give a limit. We try to get some cutoff limit to find out with signs and symptoms the correlation. Okay, at what levels the signs and symptoms of the blood pressure appear, and what could be the very severe form, what could be on the lower side. So like that. So we try to correlate with the signs and symptoms, and then after that we try to come to a level which will say that yes, this is a cutoff limit. Similarly, for the diagnosis of diabetes also, if you take the fasting blood sugar level, or if you take HbA1c level, why 6.5? Okay, as HbA1c level. So like that, you can keep asking me. And similarly for anemia also, there is a difference between males and the females. Why there is a difference? Physiologically, yes, definitely there is the hemoglobin level is usually lower among the females as compared to the males, but still they can survive, and they can also, they do not exhibit many severe symptoms at a lower level as compared to the males. So for different gender and also different age groups, we might be having different cutoff limits. And all these things we try to get from the normal distribution in the population. Now, to begin with that, if we know that this is the normal distribution, and what is the abnormal distribution? So that means if a population, we have a normal distribution of all these different parameters, and for some sample, or if I take a sample maybe from a different population and try to find out the values of those sample means some group of people, maybe the adults from a different population. So we try to find out whether the population is similar to this population or not. Then we try to do, after calculating all those different values, and then try to find out whether there is any difference between the particular sample values from that of the population value. So this we try to find out based on the different tests of significance. So this is one example which I am giving you, and this is of utmost importance because in the medical sciences, we also do a lot of research, and we have to validate those research findings by merely saying that yes, the hemoglobin level among the males is higher as compared to the females, but is there any significant difference? So the significant difference can be validated and can be obtained if we try to apply some certain statistical tests of significance. Then only we can come to know that yes, there could be a significant difference. Okay, so likewise we can say that if in a population of maybe say urban population, another is the rural population, the prevalence of the hypertension is, let us say in the urban population is around 40%, and in the rural population, if I say it is 30%. Now 40% difference, 40% in the urban and 30% in the rural, the difference of 10%. Whether this 10% difference could be similar, because it may come under normal distribution also, and whether it is different between the two groups, just so. And if you think that yes, there could be a difference, then how to find out and how to validate that? So that could be done by applying tests of significance by statistical tests. Okay, so this is how we try to come to a conclusion that yes, there could be a similarity, or this could be dissimilarity, or there could be a difference. All those things we can comment upon it. So this is the importance of these different statistics. Now, this I would like to tell you from this lesson and from this session. And before that, you need to know the type of the data we use, that is the nature of the data. In general, if we try to look at this in general, there are two types. One is the quantitative data. The first one which I have written here, the quantitative data. The second part is the qualitative data. Broadly, two types. The type of the statistical test that we apply, it all depends upon the nature of the data. Please remember that whenever a sum is given to you, then you have to first identify whether that particular data is quantitative in nature or it is qualitative in nature. The first thing that you should do. And then after that, you try to find out which type of test would be applicable, depending upon whether it is normally distributed or non-normally distributed. But for your understanding and for your undergraduate level, we only give you those which are with the normal distribution. So don't worry much about the non-normal distribution of the data. So when I talk about the quantitative data, you just try to think it like we try to find out the problem magnitude. And the problem magnitude could be, it should be measurable. And it is used mostly with, there are certain units which are used in those measurable values. And it is also sometimes called as continuous data. Now, what are these? I'll gradually come to this with example. If I talk about a blood pressure or hemoglobin or blood sugar level, then we are all measure it and we get a unit. If it is blood pressure, it is in terms of millimeters of mercury, and hemoglobin, it is in terms of grams per deciliter. Blood sugar, again, milligrams per deciliter, like that. So this is a quantitative data. It is a continuous one because the value is ranging from the minimum to the maximum level. And anybody's value can be plotted on that. If I draw a line starting from the minimum to the maximum of the values, and I try to find out someone's blood pressure within that, in that range of smallest to the maximum, I can plot that value in a line. Okay, I can locate that person's value. The hemoglobin, there may be the hemoglobin level also, maybe blood sugar level also. Similarly, I can plot that. So this type of data where the values are in continuous. So continuous in continuity. So in the continuous mode, that means like you may find whenever I talk about the continuity, you could also find the values expressed in decimals. Now 1.1, 1.2, 1.3, these are decimal points, isn't it? 0.1, 0.2, 0.3. In addition, I can have a large number. So that means 1.11119, 1.1 2222229, 1.33387, like that. It can keep on the right hand side of the decimal. It is again continuous. So that means there is no limit. There is no limit of the values. Okay. So that means the continuity could be there, the values. So this type of data is considered to be quantitative data. Please remember this. Then the second one is the qualitative data. It also gives you some indication about the vastness of the data, or maybe the how large or how small the data set is, but it does not fully quantify about it. Okay, it doesn't fully quantify, and this is usually expressed in terms of percentages. Please remember, the qualitative data usually is expressed in terms of percentages or in absolute numbers. Like gender, if in the population, after a survey, I try to find out how many males and how many females are there. So then the number, the value, I can get it. I try to extrapolate and say that yes, the males constitute 48% of the population and the females constitute 52% of the population. Oh, like that. So that means I try to get some quantity, but not exactly the quantification in terms of the measurement. But this gives you some indication about the size of that particular value. So this is qualitative, and qualitative data are usually categorical. And this categorical means, like, if we try to find out measurement in terms of the numbers, absolute counting in numbers, that is what is also known as discrete value, the counting of the numbers in 2 different groups, 3 different groups or more, and number of groups, like that. So the type of counting of numbers in different groups, that is a category. Okay, like gender is categorized maybe male and female, and also transgender or a third gender, it can also be done. And area, I can talk about in terms of different categories, like it could be urban area, it could be rural area, or it could be semi-urban area, or it could be slum area, or it could be peri-urban area, like that, different ways. But there are different categories. And in each of the categories, how many of them are there? I'm just counting the numbers. So that is giving you some indication about the vastness, or something about how large is the population in the particular category. So that is the qualitative nature. So this is briefly about the qualitative data. So when we talk about the counting numbers, then the data could be considered to be discrete. I'm just counting them 1, 2, 3, 4, 5. So this is a discrete variable, and the discrete variable will give you the countable numbers only. So please remember that. The second one is, if I talk about the next type of the variable, and that is what is known as continuous variable. And here the value is what I have told you in the quantitative variable. This is a quantitative variable. So I can divide the types of the data in some more finer aspect. First, the broad category, quantitative and the qualitative. And in the qualitative, it could be discrete. In a quantitative, it could be continuous. There's different other ways of classifying the data. Now, the continuous data, it results from infinitely many possible values that correspond to some continuous scale that covers a range of values without gaps, interruptions, or jumps. Like an example here for hemoglobin, I can start from 1 up to maybe 19, even 20, 21. So a range is there from minimum to the maximum, and anybody's hemoglobin can be plotted in this. I can look at them. So that is a continuous variable. So similarly, the discrete variable, the number of students who are anemic, maybe girls and boys. So if it is expressed in terms of percentage, it's 60% girls, 40% boys. So that also becomes a discrete. That becomes expressed in terms of percentages, but discrete is countable numbers, absolute numbers. The continuous one, the weight of the students. I can have the weight of the students ranging from minimum to the maximum. So, and here you can see the decimal point is here, and the unit is also given over here. So it gives you an indication that weight is a continuous variable. Now, there are again other ways of measurement and of the data. This could be nominal level of measurement. What is that nominal? Now, this is characterized by like naming or labeling or some categories. As I've already told you, this is again a part of the qualitative data. Broadly, it comes under that nominal. So naming variables. I can name different cities. I can name different villages. Okay, all those like Kolkata and Mumbai. So what is the difference in the sex ratio between Kolkata and Mumbai? Okay, so broadly, so that name is there in that that is the city, and then up in that city and how much the proportion of the particular variable of interest. So that is what is nominal. And so data cannot be arranged in an ordering scheme such as low to high. I'm just naming them different. These are all independent. Okay. So in examples, if I'm asking about a survey, and if I say how many of you stay, how many of you are underweight, somebody say I am underweight, somebody say I am not underweight. So they're different categories again. Then if I ask, say for example, how many are you anemic? Like if you have a record, medical record, and based on that record, can you show me the medical record and tell me whether you are anemic or not? Say yes or no, or I do not know. Okay, so report. So that means the responses are also given in terms of certain numbers, certain values, but which is again countable numbers. Yes, how many, no, how many, and undecided, how many of them have given this, like that. Similarly, the coverage of immunization in urban area versus rural area. How much is the difference? So that nominal level of measurement will give you an indication about the value in different categories. Now, other level of measurement is the ordinal level. So the ordinal in some order. Just remember the word ordinal. This is in an order. So that means whenever I am arranging the values in some order, this could be from the minimum to the maximum, or this could be from the maximum to the minimum. Either way, if I'm arranging them in some order. Like as an example, if there is a gradation, grades are given to the students after the examination, and it could be A, B, C, D, F. And so if I say A is the maximum and F is the minimum, or otherwise also A is the minimum and F is the maximum. So that means some gradation is there and some continuity is also there, but it gives you an indication about some order, starting from the minimum to the maximum. So this is an ordinal level of measurement. Similarly, when we talk about a socio-economic status, which is divided in terms of some groups like low, middle, and high. So that means I'm having some order in terms of the socio-economic status, starting from the lower to the higher socio-economic status. This is also an ordinal level of measurement of the data. So there are broadly two types of measurement. One is this ordinal, which is in an order, and another one is in a nominal level, and which will give you just an indication about the various categories. Okay, so please try to remember this: the nominal and ordinal level of measurement. And ordinal level of measurement is usually used in the quantitative, or maybe the continuous variable, whereas the nominal one is used in qualitative variable. Okay, qualitative data. So these are the two things that you must remember. So again, just to re-emphasize, nominal is for the categories, ordinal is if it is categories with some order. Okay, BMI starting from the minimum to the maximum, like underweight, then normal weight, then pre-obese, obese, then like that, morbidly obese, like that. All those different categories are there. So this is all about the data. Now next is about the measures of dispersion, which is also of importance. Just to revise what I think you might have had a class on it, but then you must also know what is the dispersion means. So that means these are the descriptive statistics that describes how similar a set of scores are to each other. So that means if in a population, if I am taking hemoglobin level among the males, let us say, and all the males, how much is the difference? How much is the similarity? Okay, I try to find out. And some of them might be having very low hemoglobin also. Some of them might be having very high hemoglobin level also. So that means whether they should be considered part of the population or not. So this person tells you about the distribution of the values, and usually around some central tendency. And what is a central tendency? The central tendency of the data is whenever I try to get an average or mean, if it is a quantitative data, that gives some indication about the population mean. Okay, and if it is a median means I try to arrange the values in either ascending order or descending order. The 50th person, the value of the 50th person, if I'm arranging for 100, the 50th person, the middle value. Okay, and that gives you an indication about the mid value of the various values. So that is the median and more. So if I'm trying to get the value of different individuals in terms of hemoglobin, the maximum number of people having that particular hemoglobin, like 11, many of them may be having 11, 11, 11 in a sample of say 50, if 30 of them are having 11, and some of them, maybe let us say 10 of them are having only 9 to 10, and some of them maybe another 10 may be having, say, let us say 11 to 15. So like that. So that means the number which is giving the maximum value, which is shown maximum value after counting all the different values. So the most commonly found number, that is what is known as the mode. So this mean, median, and mode gives you an indication about the central tendency of the distribution of it. Now, the distribution tells you from this central point of view how much of these different values are away, either on the lower side or on the higher side. So this gives you the dispersion, the minimum to the maximum, and around that particular median level or mid level. So the more similar the scores are to each other, the lower the measure of dispersion will be. So we try to also find out the measure of dispersion. Okay, if there is dissimilarity between the different scores, then the dispersion level will be much higher because they are widely distributed. They are widely distributed from each other. Okay, or from the mid value if I take. So that is giving you an indication about dispersion. In general, the more spread out the distribution is, the larger the measure of dispersion would be. So what are the different measures of dispersion? Now, if you look at these two figures on the right hand side, these are the histograms, those different bar diagrams which are again drawn side by side. Okay, this is what is known as histogram, continuity in continuity. Now, if you look at this, the first one is starts from 0 up to 10, and the second one is start from 2 up to 9. All right. Now, if I tell you this figure, so then how much is widely distributed? The first one, because it is away from 2 up to 0 and up to 10. So distribution is very wide in the first one as compared to the second one. So this tells you about the dispersion of the values. Now coming to the continuity about this, there are three measures of dispersion. One is range, another is semi-quartile range, the third one is variance in association with, again, standard deviation. There are some difference between variance and the standard deviation, and we are more concerned about the standard deviation, what it is. So you must try to understand that. Now range, we try to understand this range by this. The range is defined as the difference between the largest score in the set of data and the smallest score in the data set. So XL is the largest value, the hemoglobin level, let us say 19 is the highest, and minimum is, let us say 5. So the difference between these two, 19 minus 5, that is 14. This is the range. Okay. Then if I give you this example here again, the different values are given here. The minimum one is 1, the maximum is 9. So the range here is 9 minus 1. So that will be your 8. So the range is 8. Now when to use the range? The range is used for ordinal data. So that means whenever there is a data set, this is having some order, that is ordinal data, or presenting results to people with no or little knowledge about the statistics. So I can say that here this is the minimum, this is the maximum. So everybody is lying within this range of 14 or 10. Okay, so you can say like that to the people that they can understand it. Range is rarely used in scientific work. It is fairly insensitive. Please remember that it depends only on two scores, the maximum score and the minimum score. So two very different sets of data can have a similar range. So that means it does not indicate how much is the variability. So if on the left hand side, everyone is 1 and maximum is 9. Now on the right hand side, you can see 1 is also there, 3, 5, 7, 9 is also there. The different values are there. So these are two different data sets, but the range is similar. 1 to 9, 1 to 9. Again 8. 8 is the range. So it does not give you a clear picture about the distribution of the values. Now what is this interquartile range? So please try to remember that. Arrange data in an order. It could be ascending order. The first quartile is 25th percentile. Now what does it mean? If I try to arrange 100 people in an order, the value of the 25th person is what is known as 25th percentile, and the value of the 75th person in that order, either ascending or descending order, is the 75th percentile. The difference between this third quartile and the first quartile is what is known as interquartile range. The first and the third, not the first and the fourth. Okay, please remember this. So this gives you about the interquartile range. And if I talk about a semi-interquartile range, so that means the value of the interquartile range divided by 2. Semi means half, let us say the half of that interquartile range. That is what is known as semi-interquartile range. So here this gives you an indication. The value of the third quartile and subtracted by the value of the first quartile divided by 2. That is half of that interquartile range. As an example, if I give you this value, I'm just showing you. Yeah, this is the value on the right hand side. The table is given to you. Let us say the value of the 25th percentile is 6 and 50th percentile is 12 out of 12 number of students. So the third value is 6 score, and the middle value, that is for the 6th student, it is 12, the 50th percentile, and the 9th value is 30th. So the interquartile range here is 30 is the value of the 75th percentile, and the value of the first quartile, that is 6. So 30 minus 6. So that is 24. Now, if I talk about a semi-quartile range, half of that. So that is 12. So this is giving you an example of the semi-interquartile range. Now, when to use this, it is used when there is a skewed data. It is insensitive to the extreme scores. But it is skewness. When the data is not normally distributed, the data could be either it could be skewed either towards the left hand side or towards the right hand side. This could mean the distribution is either, it could be, when I talk about the normal distribution, it is a bell-shaped curve. I'll come a little bit later to this. So if it is bell-shaped curve, the bell, so the bell-shaped curve, and if the bell-shaped curve, one half is, say, let us say it is because of the distribution of the various values, it is tilted toward the left hand side or it is tilted toward the right hand side, then this is what is known as skewness. So that skewed data, we use this semi-interquartile range. Now coming to the next concept, mean absolute deviation formula. Now, what does it mean? Now, this symbol, it gives you an indication of a summation, and in this bracket we have x bar, which is the mean value, and x is the value of any other person in the particular population or particular sample. All right. So the difference of that particular person from that particular mean. So for every person from the mean, that difference is taken and it is summed up. So that gives you this indication, summation. All right. Summation of the difference of every individual's value which is different from the mean, and divided by n. N is giving you an indication about the size of the sample. Okay, it could be 100, it could be 50, it could be 30, whatever is the nature of the sample that you have identified. So based on that, if I try to find out the difference, sum up of all the differences divided by 2, this gives you mean of absolute deviation. How much is the deviation from the mean? This gives you an indication about the difference of the value from the mean deviation. And absolute means it is absolutely, because every individual is subtracted from the mean, the value I have got it. And so I'm adding those differences. So that is why it is known as absolute deviation, and mean because I'm adding them together and divided by the total number. That is n here. Now for the computational formula, let us try to look at this figure. X on the first column, these are different values of different persons, 9, 8, 6, 5, let us say it is hemoglobin. Now I square these values, then it is like you can square each of this, 81, 64, like that. Then if this mu is usually indicated for the population mean or mean here. For this example, it is a mean. So that means if you, for the mean, what you do is on the first column, add up all these values, that is summation, it comes to be 42. And how many of them are there? N is 6. 1, 2, 3, 4, 5, 6. So 42 divided by 6. So here you can see at the end, at the lower side, I can see one value, that is 7. So this is the mean. Now, how much each value is different from the mean? So for the first value, it is 2. 7 minus 9. Then 7 minus 8. 7 minus 6. But it is showing the negative sign. So that means if I'm subtracting it from the value, the particular mean, so 9 minus 7, it is 2. 9 minus 8, then the 7 minus 9 minus 7, then 8 minus 7, 6 minus 7, then it becomes minus 1, 5 minus 7, minus 2, then 8 minus 7, 1, like that. So you have got the values of positive as well as negative. If I am trying to find out the variation of each of the values from the mean, okay, the mean value here is 7. And if I add up these different values, this ultimately the difference comes to be 0. Okay, so that means absolute difference of all these different values from the mean, it comes to be 0. But if I square this value, now what will I get? X minus mu square it. And so this 2 square is 4, like that. So ultimately I am getting a positive value summation, that is 12. So this is used. This is used for the variance. So this is what is known as variance. Variance is how much each of the value is different from the mean and how much it is square. Okay, so that gives you the concept of variance. I'm coming to this. Now, so just to give you what is variance, variance is defined as the average of the squared deviations. So in the previous example, the last column, I have squared the deviation, and if I'm so total deviation, I'm summing up and then divided by total number, so that gives you the average. So that means this shown by this sigma square, and so it's equal to summation of x minus mu. Let us say if the value is not given, then it could be the population mean. Usually it is known the population mean, and how much each value is different from the mean, you square those deviations and divided by total number, so that becomes a variance. So please remember this. Variance is giving you an indication about the average of the square deviations. Now for the computational formula, so here I told you the summation is 12 and divided by n, that is 6, so the variance here is 2. Okay, so this variance takes into account, it gives you the variability of these different values within this sample. All right, and if I take only the absolute values, then there is no such variation is there, only 0 is there. So that's why we try to square these values to get the values in positivity. So what is the meaning of this variance formula? I'm just giving it to that. It says to subtract the mean from each of the scores. The difference is called a deviate or a deviation score. All right, each value from the mean, that is a deviate. Then this deviate tells us how far a given value or a score is away from the average score. Now, what is that mean? Mean is nothing but the average. So how far it is from the mean? How much is the difference? Then a deviate is a measure of the distribution, dispersion for the given score. So this deviate gives you an indication about the dispersion, how far it is away from the central tendency. Here it is the mean. Okay, the central tendency we have taken here the mean. From the mean, how far it is away? That is 1, 2, 3, 4, 5. So 5 is there, then it is more. It is the value is more dispersed, and it is 1. It is very nearer to that median, that mean value. That is the mid level. So that shows an indication about the nearness of the value to that particular middle value. Okay, so this gives you an indication about the dispersion. So why why can't we simply take the average of the deviates? As in that example, I have told you the sum of the deviates could be 0. Right? If I just take the absolute differences, everybody adding up plus and minus, then it becomes 0. So that's why we try to get the value of the variance in terms of squaring. So you can look at this. If I talk about the variance, then it is not equal to this. That means only the absolute differences summation and divided by n. N is the total number, okay, of the sample. So this is not the formula of variance. If I talk about variance, then it should be squared. This x minus mu, it should be squared. Everybody's number. So that number, that summation, sum up and then divide by the n. So that is why this is not a formula for the variance. Now again, variance is mean of squared deviation scores. So whatever the values you have as a deviation, you square them, you take the summation and divide by the total number, it gives you the mean value. Okay, the squared one. The larger the variance is, the more the scores or the values deviate away from the mean. Similarly, if the variance is small, then either less the scores, the values deviate from the mean. Now coming to the concept of the standard deviation. Please remember this. So far we have talked about the deviation and after it variance. The variance is sigma squared, and the sigma square is summation of all those squared values divided by n. That is the variance. Now what is the standard deviation? Now if you know up to variance, the calculation, then standard deviation is easy. So when the deviate scores or values are squared in variance, the unit of measure is squared as well. Okay, whenever we are squaring the values, so their units are also squared. So we try to remove that squaring. So that means if weights are measured in kg, the variance of the weight would be expressed in terms of kg square. Okay, we don't want this type of squaring. So this squaring of the units are often awkward to deal with the square root of the variance is often used instead. And that square root of this squared value, that is the variance, is what is known as standard deviation. Okay. So standard deviation is the square root of variance. Now we have squared, and so again to come back to the normal, again, so that is what is known as the standard deviation. Okay. So standard deviation is equal to under root of the variance, and variance is standard deviation square. So it is sideways, which you can have this. Now the concept of standard deviation, again, this is the measure of variation of values about the mean, and the average deviation from the mean again. So it is also, you can remember how to calculate this by root of mean squared deviations, RMSD. So that means you start calculation from the right hand side. Deviation of a particular individual, the value from the mean, you square it, but whatever the deviate, square that value, and after that take the mean of those squared values, and after getting that is up to this much is known as what is known as the variance. Then take the root of that, the root of the variance, that becomes your standard deviation. So the simple mnemonic you can remember, RMSD, root mean squared deviation, just to calculate the standard deviation of values. The computational formula, the variance is given like this. You can note down this sigma square for the variance. Okay, sigma square is usually considered with the variance. Summation of x square minus, in bracket, summation of x. X is the different values up to n, different from 1 to n, and square this divided by n, then divided by n, and it is also equal to summation of x minus mu. Mu is the population mean or mean of the sample if the population mean is not given. Square divided by n. This is what I have told you just now. And this can also be written this way on the left hand side. So this is the variance. So this sigma square is the population variance, x is the score, mu is the population mean, and capital N is the number of scores or the total number of values. Again, coming to this computational formula, we have talked about this, the last one, summation of x minus mu square for each of the values from the mean. Okay, so we have got the absolute value is summation is 12. Now, if you look at this, we can substitute these values, x square, summation of x square. I'm just going back, x square values, the square values, this is 306. Okay, 306. Then summation of x, and let us have this figure is 42. Again, let's go back to the previous example. That is summation is 42 here on this first column, x summation of different values, 42. Again, divided by 6 is the n. So if you compute all these, after that you get a value of 2. All right. And similarly, on the other hand, I can also do it like this. Simple way, summation of all the deviations squared, that is 12, divided by 6, that is your n, that was 2. So both this formula giving you the similar answer, that is the variance, that is 2. Okay. So what this formula can be used for the variance. Now, if I talk about the standard deviation, then it will be under root 2. That will be your standard deviation. Under root of this. Okay, that will be your standard deviation. And if I'm having a table which is having the frequencies are also given with different ranges, like say 10 to 15, 16 to 20, 21 to 25, like that. And for different values, if I take the mid value, and that mid value is what is known as this, the past midpoint is the X is the class midpoints. Okay, 10 to 15, that will be 12, but 12.5 is the class midpoint. Okay, so use the class midpoint as the X values. This is the value of the X, that is class midpoint. If it is 10 to 15, I'm taking 12.5. That's the class midpoint. And the frequency is the number. 10 to 15, how many are there? That number is what is known as the frequency. So this is the formula which is used if the data is in a range and in different classes, okay? So under root small n in bracket summation, again in first bracket, f is the frequency multiplied by x square is the midpoint of that particular class, minus, then third bracket, then summation in bracket, f is the frequency minus multiplied by x, and the first bracket closed, the third bracket is also closed, and square it. And here it is, within this, within the first bracket, the x is square, and here the square is after the third bracket. Okay, so divided by n into n minus 1, this gives you the standard deviation of the frequency table. Now, whatever I'm telling you right now, this will be practice, and whenever you come to the department during your practical posting, our residents will be giving you sums related to all whatever I got so far. Okay, how to calculate the standard deviation, how to calculate the mean, median, and mode, and all those things. That will be done in a practical mode. Now the variance of a sample. The sample mean is not a perfect estimate of the population mean. Please remember, what is the sample? Sample is a group of people from the population taken at random. That is, or maybe non-random also. So that group of people, if I have a population of let us say 1.25 crores Indians, then how many samples? If I take only 100, whether the 100 is representative of the total 1.35 crores? Absolutely not, isn't it? Every one of you must be agreeing with me that only 100 people selected out of 1.35. How to say that? Why do you say only 100? Why did you take only 100? This is not an adequate sample. You may ask, isn't it? So like that. So if I am having only a small sample, the sample mean is not a perfect estimate of the population mean. So that is why the sample mean does not always correlate with the population mean. All right. So to get an adequacy of the proportion of that population, representativeness of the population, but for a particular variable, let us say I'm talking about anemia prevalence, then based on the anemia prevalence, I'm having some percentage, let us say it is 70% of the all the adults are anemic. Let us say that. Okay, 70% is quite a big number. Now, if I'm trying to get 70%, then I'll be having some adequacy of sample is also necessary. Okay, so the sample size determination is another way, which I'm not covering in this. So based on that proportion, based on the prevalence, I'll try to calculate the sample size, and it will give an indication that this much sample is required for a representative sample of so many people in the general population. Okay, so like that. Otherwise, the sample mean is not a perfect estimate of the population means. The formula for the variance of a sample is slightly different from the formula of the variance from a population. So, and here it is. And so this is the S square is the variance, sample mean, and let us say, sorry, the sample variance, then summation x minus x bar square divided by n minus 1. The large population, then subtraction of 1 does not give much of a significant difference. So that is why n minus 1 is also used. It's the variance of a sample. S square is the sample variance, x is the score, x bar is the sample mean, and n is the number of score. Okay, for a particular sample. So this is the formula for the variance of a sample. And if I'm trying to get the standard deviation of the sample, then I will take the square root of this. Okay, root of this, the whole thing on the right hand side. So there are some symbols that are used for standard deviation. For a sample, sometimes in the textbook it is written small s, and population in the book it is written sigma. Then some graphic calculators use capital SX, small x, and on the right hand side it is like this the sigma x. Then some non-graphic calculators also use small x, then sigma n minus 1, and on the right hand side some for the population it is capital X, sigma n, like this. So there are different symbols are used, but for simplified purposes, let us say we can either say it is standard deviation SD, capital S and capital D, or this sigma can also be there. So articles in professional journals and reports often use capital SD for standard deviation and VAR for the variance. Okay, please remember this. The last line is important. Now, if a population value is widely diverse and widely dispersed, it could be from the normal, that is when I talk about normal, that is the bell-shaped curve like this. And from the bell-shaped curve, if it is positively skewed, is if on the right hand side the large number of values are put on the right hand side for the particular sample, then it is positively skewed. I think negatively skewed is when on the left hand side the large number of values are there. So the maximum of the values are trying to pull back the values to the left side. So that is what is known as negatively skewed values. Okay. So skewness is a measure of symmetry in the distribution of the scores and the values. So now let's come to the normal distribution, which is also known as the Gaussian distribution. What are the various features of that? Let's try to understand that. So you can see here there's a bell-shaped curve, the blue colored one, the dark color, and you can see the baseline. And if you see the tails means left hand side tail is here and the right hand side tail is here. That is where the arrow is also given. So the tails, the lines of the curve, it does not touch the baseline. Please remember this. This is parallel to the base. And secondly, the mean, median, and mode, they lie on the same plane. Sorry. So that means if I have a mean of this sample and median also and the mode, the values will be similar. That is what I want to say. So that means if it is normal distribution curve, the first thing shape is bell shape and the tails do not touch the baseline. Mean, median values, the central tendency values, they are similar, they lie on the same plane. These are some of the characteristics. In addition to that, within one standard deviation, I mean from the central value, from the mean, if I take one standard deviation, minus tells you lower side and plus tells you on the higher side. Okay. So the mean plus minus, I can say plus is on the right side, left hand side the minus. So the whole thing, one standard deviation will cover a population of 68%. That means if I am having a sample of 100, 68 of them would be lying within this one standard deviation, the values of the 68 people. All right. Then if I talk about two standard deviations, so two standard deviations will be little away, the value of two standard deviation. So then 13.5 on the right hand side, 13.5 on the left hand side, you can see here two standard deviation values. So it becomes wider now. So from the left hand side to the right hand side, and whatever the values are lying in this curve within this two standard deviation would be approximately, that will be for about 95% of the sample numbers. Okay. So if I talk about three standard deviation, then it will come very near to this 99.97. Like that. It will come very near to the tail end of this, border ends. Okay. So this will give you an indication about the normal distribution law, the empirical rule. So usually for all statistical purposes, please remember, we don't take the whole 100% population or 100% of the sample. So we take only up to the two standard deviation. So that means we take that 95% of the values are normal. So that is what we try to assume as per the rules of the statistics. Please remember that. So that means if I talk about this normal distribution curve, 2.5 of this would be lying outside on the right hand side, and 2.5% of the total number would be lying on the left hand side. Combinedly, it will be 5%. Okay. So this is the cutoff limit where I would say that this corresponds to the p-value, the probability value of a person which is either part of the population or part of the sample or not. So then this is the cutoff limit. So that 5% limit, which is equivalent to 0.05. 0.05, 5% is equal to 0.05. I am repeating again and again. Please remember this. The p-value which is usually taken is corresponding to this 0.05, 5% level. If the value, if I'm trying to find the value of a sample population and it is lying outside this 95%, then I would say it is away from the not a part of this population. So then I say it is statistically significant. Okay, just to give you the vague concept of statistical significance. I'll come to this later on in the presentation. Okay, so the third one, which I told you about 99.7, will lie within the third standard deviations. Please remember this, almost nearly 100% of the values, not exactly 100% here also. So statistics is all about the probability. Please remember that, and we try to find out whether the probability is okay or not. Sometimes it could be incorrect also. Sometimes statistics does not tell you correct picture as well. So there are ways. That is the other side of the story. But still, we try to concentrate on the Gaussian normal distribution curve. What are the various characteristics of that? Now coming to the statistical inference. So this is the third part. Little bit, I think you have come to know about the normal distribution and how I try to compare a normal distribution with some other population, two different populations, and whether they are similar or not, whether they are dissimilar, whether they could be part of the population or not. That I try to find with using the statistical test. So now, coming to this different aspects of this statistical inference, there are two important questions which are raised in the scientific studies. How reliable are the results obtained, whether it is just an estimate or whether it is likely to be true with what is actually occurring in nature. And second one is, how probable is it that the differences between the observed and expected results on the basis of the hypothesis have been produced by chance alone? Okay, please remember this. So the probability. Now, if I'm trying to find out, let us say that the prevalence of diabetes in the urban area is, let us say, 30%, and in the rural area it is 20%, similar to the blood pressure, which I've given you an example. Now the difference of 30% and 20%, whether that 10% difference is it very large enough to say statistical significance or not, or whether it is just an estimation, or whether it could be part of that normal distribution of the different diabetics. All right. So that would be done by doing this, by applying the various tests of significance. Please remember. So by computing this different statistical tests, I would like to say whether the difference is occurring by chance or it is actual difference or not. So there are different steps in the hypothesis testing. I would like to find out initially, whenever I try to do some study in the population, I have some hypothesis in mind. What is that hypothesis? Like I would say whether there is a, I can formulate a null hypothesis. So you have to understand what is a null hypothesis or what is the alternate hypothesis. Null hypothesis will tell you the assumption before conducting the study itself, I am assuming that there will not be any significant difference between the two groups. Okay, in terms of the particular variable of interest. So that is null hypothesis. Null hypothesis here is the similarity. So there is no difference. That is the similarity. So null hypothesis. And if on the other side, I can say, as an example, anemia is more prevalent among girls as compared to the boys. Okay. So if I start like this, I'm already having that notion, the perception that girls are already very highly anemic as compared to boys. So that means there is no similarity. So then it is an alternate hypothesis. If I say there is no difference in the prevalence of anemia between boys and girls in the population, I'm assuming that similarity. Then it is a null hypothesis. Like that. Okay. So I frame null hypothesis. I also frame alternate hypothesis, which could be the possibilities. Maybe the possibilities could be the prevalence is anemia is higher among the boys. The prevalence could be another null hypothesis could be, now alternate hypothesis could be the prevalence of anemia is more among the girls as compared to boys. Okay, there another alternate hypothesis. Then the third alternate hypothesis could be, I do not know actually who is which one is more prevalent among boys and girls. So then I can say there is a difference in the prevalence of anemia between boys and girls. So this could be another alternate hypothesis. So null hypothesis usually H0 is only one. Alternate hypothesis could be more than one. All right. It could be either in terms of boys, it could be in terms of girls, it could be no similarity like that. The three alternate hypotheses I can frame from the prevalence of the anemia. Then based on that, I try to choose the appropriate test of significance, compute the test statistic, compare it the threshold value, and then after that the p-value, the probability value, and take a decision. When I say p-value is less than 0.05, please remember this. This is an MCQ question. So p-value less than 0.05 is usually considered to be statistically significant. Now, what does it mean? So the meaning of this, I'll tell you when I talk about the different tests of significance subsequently, either in students' details or in the chi-square test, how to calculate this p-value, how to locate this p-value. Okay. So these are the different steps. So as I've already told you, null hypothesis, the hypotheses are formulated to be tested or refuted. Then the null hypothesis H0 shows no difference. Alternate hypothesis could be H1, H2, Hn. When a null hypothesis is found to be false, then we say that alternate hypothesis will be true. Alternative is the opposite of the null hypothesis. There could be either a one-sided alternative or two-sided alternative. Two-sided means I told you that there is no difference between boys and girls in relation to the prevalence of anemia. The two-sided, I do not know whether it is boys, whether it is girl. Okay. So null hypothesis usually is H0, mean of, if it is quantitative variable. I'm again coming to that various previous nature of the data, quantitative. When I take the mean value, that becomes a quantitative usually. All right, mean of 1 equal to mean of 2. The second sample, mean of first sample, mean of second sample. Okay, similar. Alternate hypothesis, mean of 1 is less than mean of 2. Mean of 1 is more than that of 2, and mean of 1 is not equal to mean of 2. There should be the similarity should be there. There should be one cross over here. It is missing over here. Okay, so this is the alternate hypothesis. Now, all the statistical tests of significance, it gives you an indication. However, it should not be 100% relied upon, because sometimes it can also make certain mistakes. The test of significance can also give you wrong inferences. The example here, I am giving you a similarity with a judgment in the court. Okay. Now let us look at this. On the left-hand side, the truth is there. A person has been caught and put behind bars. Actually, he is a criminal. And however, in a crime scene, one person has been captured and has been put behind bars. He has not done anything, but he has been captured, labeling it to be a criminal, although he is innocent in actuality. Okay, now let us look at this court judgment, which is similar to the test of significance by statistical tests. The court has pronounced that person to be guilty. Now, if it is a criminal, then it is a correct judgment. Now, if the innocent person is been pronounced guilty, then it is an error committed by the court, isn't it? Similarly, the court judgment says it is not guilty. Now, the criminal is found to be not guilty because of lack of evidence, then another error is committed, and the innocent person is found to be not guilty, and it is a correct statement and correct judgment is given here. So these two types of errors can happen. Okay. So now, whatever this judgment gives you an indication about the errors which is committed by the statistical test of significance also. I'm coming to this. Now let us look at this. The actual position on the left hand side, if you look at this, null hypothesis is false. So that means there is actual difference in there. Okay, the one situation. The other situation is null hypothesis is true. That means there is a similarity. There is no difference between the two groups. Now I compute the test of significance, statistical test, and draw some conclusion. And based on the conclusion, I try to reject the null hypothesis. Okay. After calculation, after computation, I am rejecting the null hypothesis. That is showing difference. I'm rejecting null hypothesis, showing a difference is there, isn't it? So, and if actually there is a difference, and the test is also giving you and telling you that there is a difference, then it's a correct decision, which is again given by the test of significance. However, if the test of significance is not rejecting the null hypothesis, that means you are accepting the null hypothesis, telling that there is no difference between the two groups. This is by the test of significance. In actuality, there is a difference, but your test of significance says there is no difference. This is an error committed by the test, and what is known as type 2 error, which is also known as beta error. So these are the connotations given in the statistics, type 2 error or the beta error. Now, coming to the other situation, I am rejecting the null hypothesis. That means I am showing that the test of significance is giving you a meaning that there is actually some differences there, and actually there is no difference in the second condition. Actually there is no difference, but your test shows that there is a difference. Okay, so then another error is corrected, and this another error is committed, then how it is known as type 1 error or the alpha error. Okay, now this is important from the test of significance. This error is kept at 5% level. This error, it should be kept at 5% level. If it is more than that, then it is not the test of significance is not reliable. All right, the 5% level is equivalent to 0.05. And if I am not rejecting based on the test of significance, the null hypothesis is accepted, then the correct decision, that is on the fourth cell here. This is what is known as power of the test. It is also considered to be 1 minus beta. So that means there is a correct decision when I am not rejecting this by the test of significance. Okay. So the power of beta is also known as 1 minus beta. So combinedly, both this will put together will be 1. So whatever 1 minus beta will be your power of the test. What is known as the correct decision, that is power of the test. Okay. This gives you the test of significance, gives you an indication about like 80% chance, 90% chance, or 99% chance of telling that this is the result is actually correct. The result is actually correct. Okay, that is the power of the test. So try to remember this. So now coming to the different tests of significance, before that let us try to learn some aspects of your one standard deviation, the deviation value, the dispersion values. Another one which I'll be using is the standard error. So try to differentiate between the two. So now the point estimate is the sample mean is an estimate of the population mean, and the proportion. And so whatever the sample proportion is an estimate of the population parameter. These are point estimates. Okay. The population mean and the sample proportion. Proportion is in percentage or it could be in terms of mean. Proportion if it is a qualitative data, then it is usually in proportion. Now standard error. I've used the word standard deviation for a sample. All right. So standard deviation, root mean squared deviation. Okay, this is the formula, that mnemonic I have told you. So the standard deviation gives you an indication about the dispersion within that particular sample. Now, what is the standard error? Now, if in the population I try to take different samples, please try to understand. I'm trying to get different samples. Sample 1, 2, 3, 4 from different parts of the population. For each of these samples, I try to get a mean. It is a quantitative variable. Okay? And the mean of one sample, mean of second sample, mean of third sample, mean of fourth sample, different samples. They may not be similar. But the mean, if it is taken from the population, we presume that the values would be almost similar. And so the mean of one sample would be similar to the 2, 3, or 4th sample. So this means this mean values, if I try to plot under a normal distribution curve, and I try to find out the variance, and after it calculate the standard deviation, then it becomes your standard error. So that means whatever the value I am getting is the difference between the means of the different samples is in terms of some value, and that is what is known as standard error. So the sample proportion or mean tend to vary from sample to sample, okay, in a population. This is the sampling variability or sampling fluctuation. The measure of this variability within the different samples is called as the standard error. It is a simple word, not the standard deviation, but it is the standard error. All right. So please remember that standard error gives you an indication about the variability within the population. That means because I am taking different samples from the population. Whereas for the standard deviation, only one sample was taken, and then after that I try to calculate the mean and the standard deviation. Okay. So from the standard deviation, I am reaching to standard error, which is the variability between the different samples, known as standard error. There are some relationship between these two, and this is the basis for your test of significance. All right. The first one is if it is a quantitative variable, then this is known as standard error of the mean. That is an example. The example shows that the children of 3 to 12 years age group, the mean and standard deviation of the cholesterol level of 300 children is 130 and 25 respectively. The standard error of the mean of the sample size 300 is, like when we talk about the standard error of the mean, then the standard error is given by this standard deviation divided by under root n. Now here the standard deviation is 25 and n is 300. So your standard error is 1.45. So that gives you an indication about the variability if I try to project it in the population of those different children in the age group of 3 to 12 years. Although I have taken the value of only one sample here, that is 300. If I talk about the standard error of the mean, it gives you an indication about the population at large. It gives you an indication about the variability within the population. Okay. And if it is in terms of qualitative data, then standard error of proportion is used. Proportion is in percentage. Example here. Suppose in a sample of 500 atopic dermatitis patients, 140 are found to be with fatty liver. The proportion of fatty liver among these patients with atopic dermatitis is 140 out of 500. 140 out of 500, that is 0.28, or I can express in percentage 28%. Then a standard error of the proportion here is P equal to 0.28 is given like this. under root PQ by N. Now P is your proportion, that is 0.28 or 28%, and Q is 1 minus P. This is 1 if I am using in decimals, or if I am using it 100%, then it should be 100 minus P would be your Q. Same thing will be there. So under root PQ by N. So Q is either 1 minus P or 100 minus P, depending upon how I express it. I'm expressing in terms of unit 1, then it will be point decimals. If I'm expressing 100, then it will be, here it is 28. And Q is 100 minus 28, like that. So the value ultimately comes out to be 0.28 minus, in bracket, 1 minus 0.28 divided by N, that is 0.02. Or it is also, if you multiply by 100, it becomes 2%. Okay, 100, then 2%. So similarly, there are two other standard errors. If I am having two different means, and I'm trying to find out the standard error of the difference between the means. Okay, mean 1 and mean 2. Whatever the difference is there, I'm trying to calculate the standard error of the mean. Then this formula is used. The sigma m1 minus m2, the mean of 1, mean of 2, under root sigma 1 square divided by n1 plus sigma 2 square divided by n2. Okay, now all these are squared, so that is why I take this root again. So that will be similar to that of the standard deviation. Okay, so this is the standard error of the difference between the two means. So one standard deviation of one group, standard deviation of the other group, you sum up together and take the root, that becomes the standard error of the difference between the two means. Similarly, if I take the standard error of difference in two proportions, under root P1 Q1 divided by N1 plus P2 Q2 divided by N2 under root. So PQ by N1 under root PQ by N is the formula for the standard error of proportion, and it is of 1, then P1 Q1. If the second one P2 Q2, you sum up and then take the root. That will become the standard error of the difference between the two proportions. So these are the formulas which I use for calculation of standard errors. Please remember this. So now confidence interval. Concept of confidence interval is important here because whenever confidence interval is used, it is in the context of the population. It is a population parameter. Okay, the confidence interval is a population parameter. So from a random sample, I try to calculate the standard error. Then standard error, two standard error values from the mean will give you the values minimum to the maximum, that will be 95%. Okay, so that will be giving you an indication about the confidence interval. So I am 95% confident that the values will be lying, the 95% of the values will be lying within the minimum of this much and maximum of this much. So that is what is known as confidence interval. It is also known as 95% confidence interval, or if it is a sample that is your similar to 95% of the two standard deviation values, but in the population it is used and it is 95% confidence interval. That is from the standard error we calculate two standard error values, that is your 95%. Okay, please remember that. So confidence interval for the mean, if I take this previous example, the cholesterol level, 95% of the confidence interval, mean plus minus two standard error, here it is given. So plus minus means you subtract from the mean 130, the value to twice that standard error 1.45. You add that, that will be maximum value, to 127 to 133. So this is nearly coming to, let us say, rounded it to 1.5 into 2, that is 3. So 130 minus 3 is 127, and 130 plus 3 is 133. So this is the 95% confidence interval if I am getting from the sample mean and standard deviation. All right, and calculating those standard error, and then after that giving it in terms of plus minus 2 standard error. So means that there is 95% chance of population mean of the cholesterol in the 3 to 12-year children to be included in the interval of 127 to 133. So this is similar to the sample mean plus 2 standard deviation. If I'm using the standard deviation values, then the values would be ranging from, you can see here, 130 to 50 or 80 to 180. Then 95% range of observation in the sample analysis. Okay, this is for the, if this standard deviation is 25. Okay, 50. So that means 130 minus 50. So that will be 80, and 130 plus 50, that will be your 80. Okay. So, so this value 80 to 180 is the 95% range of observation. This shows the clear distinction between interval of observations and the confidence interval. This is the interval observation, range of observation in the sample is given by the standard deviation. However, it is in the population, then it is confidence interval. This is the two difference. So confidence interval is proportion. If I am talking about the proportion, again, P plus minus 2 standard error. Please remember this. And P, that was 0.28, that was the prevalence. Then 2 into 0.02, it comes to 0.24 to 0.32. If I am converting in percentage, 24 to 32%. This means that there is 95% chance for the actual population of the proportion of fatty liver to be included between 24 to 32%. Now, the confidence interval described as 9% confidence interval specify a level of certainty leaving the rest 5% to fall in an uncertainty region. So that is why I have left out this 5%. Why I'm not taking the 100%. So that's what I told you in the initial also, in the beginning also. The statistics is all about your probability, and we take the presumption of 95%, and then we try to predict whatever is occurring within the 95% value is correct, and others are outside there. So the inference based on the uncertainty level is the subject matter of the hypothesis testing. So now these are the two steps of identifying different tests of significance. The simple way, first thing is try to find out whether the different values given in a sum is normally distributed or not. Usually it is given for you, and that is what is known as Gaussian distribution. And if it is normally distributed, yes. If it is normally not distributed, that is skewed data, then no, then different tests of significance are. So if it is quantitative data, please remember, quantitative, measurable value, having some units, all right, and mean, that is two means. The means is also calculated from the quantitative variable. So if it is unpaired, then we test student treated for unpaired data, and it is paired, it is student treated for paired data. What is the pairing means? Again, you have to remember very clearly, pairing is not between 1% of one sample with the other person of the other sample. It is not pairing. Pairing is for a single individual. And pairing is a single individual. Usually it is done in the context of two readings for a particular person. Okay. Let us say unpaired is if I am taking for the boys the value, if I am taking for the girls another value. They are two independent groups. Then these are unpaired. Okay, please remember that this is unpaired. Value of the boys, the value of the girls. Hemoglobin level among the boys, hemoglobin level among the girls. They are two different groups. They are unpaired. When I say paired, that means some intervention is done and then try to find out the effect of it. I give, let us say, ferrous sulfate, okay, iron tablet to the group of boys. Before giving iron tablets, I try to find the hemoglobin level. It is mean is 12 grams per deciliter. After 3 months of giving iron, I take another blood sample from each of them and measure the value. It is 13%. So that means from 12 it is increased to 13. Okay. So for each individual, there will be some differences. On the baseline, someone will be 12. And afterwards, it will be 13. In the baseline, someone will not be having any change also, 12 before giving iron and 12 giving after iron. So like that, there will be differences in the population, in the boys also. Okay, but ultimately I am summing up everyone else pre-level and the post-level, post-intervention level. Difference is usually 1. Okay, so then the two values of each individual is considered to be paired value. Considered to be paired value. In those instances, I do this student's t-test for the paired data. And for the other unpaired data, that is, if I am not doing any intervention, I am just trying to observe the difference between the two groups, between boys and girls, then it is unpaired data. So then it is what is known as students t-test for the unpaired data between boys and girls. Okay, try to understand that. Now, this is what I will be telling you how to calculate that. Now, if I am also having another group which is non-normally distributed value, then I try to do the unpaired. There will be two different groups and non-normally distributed values. Then the test is known as Wilcoxon rank sum test. And if they pair data, that is what is known as Wilcoxon sign rank test. So it is signed is here. Sign means whether it is paired means before and after. Okay. Whether it is declined or whether it is improved. Somebody might be values may be minus, it may go to minus, somebody may be on the positive side. So that is why it is signed. Okay, plus minus. That is signed. So Wilcoxon rank sum test, Wilcoxon sign rank test means equivalent to that of the t-test when the data is non-normally distributed. For all practical purposes, will not be giving any sums related to this non-normal distribution. Now, how to do this? So please try to understand this. Again, the theoretical and more practical sessions will be done in the class when you come for the practical sections, sessions in the from 9 to 12 in the departments. So we'll be talking about this. So comparison of mean with a pre-specified value, one sample t-test. Pre-specified value is from, if it is a pre-specified value, usually of the population. All right. Now we try to calculate t value, this small t. Please remember that this is not capital T. And t value equal to, in bracket, the value mean of this sample, that is x bar, from the population mean, that is mu. The difference in the mean of the sample from the population, okay, divided by standard error of the mean of the sample. So this is a simple formula. Just to remember, the difference between the two means from the population of the sample divided by standard error of the mean of the sample. That means the difference is trying to be projected in the form of, in terms of the standard error of the mean. How many standard errors? Okay. So this gives you the t value. Based on the t value, we also have already prepared t distribution tables. I'll be showing you the t distribution table also. Okay, the t value, different values if we normally distribute. So let us take this example. The hemoglobin levels of 15 HIV positive neonates. The sample size here is 15. The levels of hemoglobin in grams are given, and the mean and standard deviation of the series is 13.9 and your standard deviation is 1.4. Okay, the mean is 13.9 and standard deviation is 1.4 for these different values of the hemoglobin among the HIV positive. Now we got another value, pre-specified value, that is for the population value, normal newness value, and it is presumed to be normal newness value. Let us presume it to be 15.9. All right. Now your HIV positive neonate value is 13.9, and the given normal neonate value is 15.9. The difference is 2 grams per deciliter. All right. So we frame a null hypothesis telling that 13.9 and 15.9, merely 2 gram difference. There is not much of a difference. So that means there is a similarity. This is, then I say it is a null hypothesis. On the other side, I can also frame alternate hypothesis. The alternate hypothesis is HIV level is less than 15.9. Okay, this is the alternate hypothesis for this purpose, because I have already calculated it. So the alternate hypothesis 15.9 is greater than that of the hemoglobin of the HIV positive neonates, that is 13.9. So the computed T value is like 13.9 is from the population mean of the sample, and from the population, that is the neonate value is 15.9, standard error given by standard deviation divided by under root n. Standard deviation value was 1.41, and your under root n, that is here n is 15, and so it is coming in terms of minus. Now this minus value does not give any meaning to this, because we just want the difference of the mean. How much is the mean difference, whether it is very large or very less. And if it is very large, and after divided by the standard error of the mean, it is coming out to be quite large also. So that means after ignoring the sign, it is 5.49. So that means if I am talking about two standard errors in the population, that will cover 95% of the population. Okay, the standard error. And so whatever the T value is in terms of standard error, and so that standard error is the value is coming out to be more than 2 here. So it is much more higher. So that means it is away from the population. All right. So yeah, we use another term which is known as degree of freedom. So we try to calculate the degree of freedom. The degree of freedom here is n minus 1 is number. N is the sample size. Minus 1 is the degree of freedom. So 15 minus 1, it becomes 14 degree of freedom. Now the critical value. I told you that there is a T distribution table. And from the T distribution table, I try to locate this value 5.49. Okay. And at p value 0.05 level, that is 5% level. I'll just show you this, what is the T distribution level. Now, this is the T distribution table. The previous example, I showed you the T value, that is calculated T value is 5.49, at degree of freedom 14. Degree of freedom is n minus 1. N is here is 15, and 15 minus 1 is 14. Okay. I try to figure out the corresponding value of P level for this 5.49 in the T distribution table at degree of freedom 14. So look at this T distribution table. The upper one, we try to find out for both ends of the curve. That is what is known two-tailed. That is why it is known as two-tailed, both tails of the curve I am considering. If I am considering only one side, then it is one tail, which is not usually done. For all practical purposes, this is done only in certain specific conditions where the scientist is trying to find out either on the higher side or on the lower side. Okay, in those instances, then only the one-sided one-tail T distribution value is used. Now, if you look at this T distribution table here, this one 0.05 is the 5% level, that is P value 0.05%. The T distribution, the various levels of T at different levels of degree of freedom here on the left hand side. So that is DF is degree of freedom. Now, in the previous example, the degree of freedom was 14, and the corresponding value for T equal to 0.05 is 2.1. Okay. The calculation showed the value of T 5.49. To locate that 5.49 in this distribution table at the level of degree of freedom 14. If you look at this, I'm just showing you with this arrow. There's a 1.7, 2.1, 2.6, 2.9. So if the T value is 2.9, then the corresponding P value here on the top upper level is 0.01. So that means for each of the different levels of significance level, p-value, these are the p-values. 0.1 is you multiplied it by say 100, then it becomes 1%. Then next one is 5%, like that. But we are interested in this cutoff limit 0.05, and 0.2 is less than that of the 0.05. 0.01 is less than that of 0.2, again less than that of 0.05. So the way the values, it is going away on the right hand side, away, okay, and the higher the values, that is more than 2, that is 5.9 we have. So the corresponding level of p-value would be somewhere here, all right, and the corresponding p-value would be much lesser than this, because the p-value keeps on decreasing on the right hand side. So that means whatever the values of p on the right hand side, this is less than 0.05. Okay, so the corresponding value of 5.49 would be maybe 0.001, which is much less than 0.05. So p is less than 0.05. That shows that at degree of freedom 14 there is a significant difference. So that means the computation done in the previous example, okay, so at degree of freedom 14 the cutoff limit is 2.1 and your 5.9 is much greater than 2.1, which is on the right hand side of the p-value. So we say that the calculated value of t is more than the predicted value, and the hypothesis is rejected with p-value less than 0.05. So this is how it is written, the inference p less than 0.05. So this is interpreted as hemoglobin, mean hemoglobin level in HIV positive neonates is significantly lower than that of the level in the normal neonates. All right. So this is the inference. So that means there is significant difference. So this is how we try to prove that there is a significant difference between the hemoglobin level of the normal of the HIV positive neonates as compared to the normal. Okay, this is done by the t-test because this is a quantitative variable. Everything is given in value. This is a continuous one. So we choose that t-test. Why it is unpaired? Because it is one sample which is different from the population. Okay, which is unpaired. Okay. Now coming to the example of the two samples. There are two samples. Let us take this example. To compare mean systolic blood pressure levels in type 1 diabetic children as compared to the control group. The control group is that those who do not have any diabetes. So here in this table you can see the mean systolic blood pressure among the diabetic group 112 and among the control group is 116. It is a little higher. All right. And the number of children for each of the group is 25 here, N1 is 25 and N2 is 25. And your standard deviation is also given over here, 9.6 and that is 7.04. Now, if you look at this, if I take this, now it is two samples, okay. So standard error of the difference between two means will be used. The difference in the mean, p-value equal to difference in the mean of sample 1 from that of the sample 2, that is 9.69 and 7.4. That is, oh sorry, this is the standard deviation. Mean is 112 and 116 divided by standard error of the difference between the means. Now standard error of difference between the means I have told you is under root sigma 1 square divided by n1 plus sigma 2 square divided by n2. The other way of calculation here is it is given here, more precise one. So combine standard error, okay, combine standard deviation and multiply by under root 1 by n1 plus 1 by n2. Now what is this value? It is given over here. You can note down this under root of n1 minus 1. It is very large sample, then minus 1. It does not make any difference. That is for making it more precise. So 1 is just subtracted from that n. Otherwise, n1 s x1 square. That should have been done. But then n1 minus 1 in bracket close, capital S square, that is your standard deviation of the first group, x1, then plus n2 minus 1, n2 is the sample size of the second group, that is control group, and S2 is again of the second group, okay, standard deviation, divided by n1 plus n2 minus 2, okay. Now, the degree of freedom whenever two samples are given, independent samples are given, which is given by this n1 plus n2 minus 2. In the previous example, only one sample was there, so only one value was there, so n minus 1. And here two values are there, so n1 plus n2 minus 2. All right, so this is the degree of freedom. So you have to calculate first the degree of freedom. 25 plus 25, that is 50. 50 minus 2 is 48, the degree of freedom. And at that, we have to calculate the p-value based on these differences in the mean. Okay, how much it comes? Let us see. So x1 bar, x2 bar are the mean systolic blood pressure, and capital SX1 is the other standard deviations of the observation in the cases and controls. And in the pooled standard deviation is capital S x1, x2. Degree of freedom is n1 plus n2 minus 2. So students, p-value is computed by this formula is the mean of diabetes, mean of the control, 112.6, 116.2, divided by standard error of the difference of the mean. Okay, combined. This is the combined standard deviation, that is the pooled standard deviation. Okay. Given by the formula. After calculation, it comes out to be 8.4. Multiplied by under root 1 by n1, that is 25, 1 by n2, that is again 25. So this is these are the values, and so it comes out to be minus 1.5 or 1.5 after ignoring this sign. Now this sign is ignored because we only want absolute difference. Okay, for a t value only. And t. From this also you can see that it is less than 2. So then if it is less than 2, then it is a part of the population. So there is no significant difference between diabetes and the control group in terms of the blood pressure. So if we take the t distribution tables at degree of freedom 48, the value is 2. Now 1.5 is lying on the left hand side of this one, 2.01. So I just give you that t distribution table here. A degree of 48, how much is the critical level? At p value 0.05. Now you can look at this 40 and 60. So nearest one is 40, so take that 40. So 2.02 is the critical level. And your observed value is 1.5. Okay. In this example, so 1.5 is lying on the left hand side, 1.6 again lying on this side. So that means this 1.1 is already greater than 0.05. Okay, so then again it may be 0.02 here, corresponding p value level. Or the 1.5 could be. Alright. So your p value is, whatever is the value here is greater than the p value, that is 0.05 level. So that's why there is no significant difference. Alright. So the result is not significant. Ultimately, the null hypothesis equality means is not rejected, it is accepted, and so the result is not significant. So this is how you interpret. Now the third one. If you know the first example, then it is very simple. It is similar to that. Now I am doing it for the paired value. Paired value is before and after. So here, these are the different values of FEV1 for asthmatic before giving a drug. Okay, before intervention. These are different values on the upper one. Before intervention, these are the different values of FEV1 of 15 different patients. And after giving the drug, these are the FEV1 values. And so, what you get the before and after for each individual. So it could be like from before, how much is the difference? So it is negative. This is important here. The difference in terms of absolute value is important. So either it is negative or it is positive. It is important. So the first value is negative, likewise you can see, and this value is 0.9 is positive, and next one 0.3 is also positive. Improved, that means it is improved, and negative is negative shows that there is an improvement, and positive shows that there is a decline from 76 to 75. Here it is 0.9. Similarly, 0.3 from 91 to 90 it is decline. Others it is improved, 88.3 to 88.9 minus points like this. So null hypothesis, there is no significant difference between the values FEV1 before and after intervention period. Now, the test of significance in this case becomes one sample t-test, and the test is applied on mean of the differences. So here what you do is, whatever the differences are, you add up plus minus divided by 15, that becomes mean of the differences. Okay, and standard deviation of difference you can get from this. So based on that, if you do that, so the mean of the differences is given over here divided by standard error of the mean differences, that is standard error is standard deviation divided by under root n. So it becomes 0.6. So we ignore this for the t value because we just want to know how much is the difference. So from the t tables, the value of 14 degree of freedom is again 2, and this value is 6 going on the left hand side of the t distribution table. So this value is much less than the critical value, and hence the null hypothesis is not rejected, it is accepted. So it is interpreted FEV1 before is not significantly different from the after intervention. So that means the drug has no effect on the asthma. So this is how you interpret. All right. So this is about the paired t-test. Now coming to the next group of data, that is qualitative, is last one. And I'm only focusing on chi-square test. Please remember that all this will be asked in your examination. All right. So if the qualitative data unpaired, the similar one, two different groups, I'm trying to find out two different groups, the chi-square test. And if the sample size is very less, it is Fisher-Exec test. I will be considering only the chi-square test. And if the paired one, that is before and after, for the same group of individuals, it is McNamara chi-square test and kappa statistics used whenever I try to find out the similarity or the concordance between two groups. Okay, the kappa statistics used. But this will not be done for you, and we'll be considering only the chi-square test. So please take this example. The chi-square test depends on the way data is collected. It is for the qualitative data. On the absolute number, the countable numbers, which is also known as discrete data, okay, or nominal data, that is naming data, group data. So if I make a 2 by 2 table like this is the variable. Like variable could be smoker. One is category 1 could be smoker, category could be non-smoker. Okay, and type 1, type 2 maybe, let us say it is lung cancer present or absent. So A, B. So category 1 among the smoker, total smoker is A plus B the total. Out of the A are the lung cancer cases. Category 2 among the non-smoker, C are the lung cancer cases out of total of C plus D. So the total of the two groups is A plus B plus C plus D. That is capital N. So this is 2 by 2 table. The simplest way to do is, from this we calculate the chi-square statistics by the formula chi-square equal to, in bracket, AD minus BC whole square. That means AD multiplication of AD minus BC bracket close square multiplied by total N, ABCD. Okay, divided by the sum totals of the rows and the columns, multiplication. So in bracket A plus B, you can see A plus B the sum of this smoker, multiplied by C plus D non-smoker, multiplied by B plus D, that is no lung cancer cases, and A plus D multiplied by this, that is lung cancer cases. So this gives you chi-square value. Similar to T value, we also have another distribution table for the chi-square values. Okay, I'll show you that one also. So the Pearson chi-square value is In short, n is the total number multiplied by AB minus B square divided by A plus B multiplied by C plus D, A plus C, B plus D. Similar way, okay, which I have already told you. A plus B is the sum total of this first row, second row sum total, then the column, first column, this second column. Okay. So now there could be some corrections are also done, which is known as yes corrected, which is usually not given for you, but yes corrected is whenever the observed value or the extracted value is less than 5 in any of the cells, then it is known as then it is considered to be yes corrected. Okay, less than 5 is lesser sample size. Okay, that gives an indication. On the total value, you minus 0.5. But this is not done for you. Okay, but then for your just knowledge only, yes corrected is also done whenever the distribution value in the contingency table is less. So the example here, two groups, boys and girls, anemia, non-anemia, the totals. The chi-square value would be n is 247 multiplied by AD. A is 21, D is 81, minus BC 94 into 51, BC square divided by the all this 72 multiplied 175 multiplied 115 multiplied by 132. This becomes 12.35. Now here we also calculate degree of freedom in chi-square, and the degree of freedom is equal to number of rows minus 1 multiplied by number of columns minus 1. What does it mean? Now in this 2 by 2 contingency table, we have 2 rows, boys and girls. So 2 rows, n is 2 minus 1 multiplied by how many columns are the important column? Anemia, present, absent. 2 columns only. So 2 minus 1. So it is, if it is 2 by 2 contingency table, then your degree of freedom is 1. 2 minus 1 multiplied by 2 minus 1. Okay. So at 1 degree of freedom, you try to find out the corresponding chi-square value and compare this with the corresponding this chi-square value, and then try to find out whether it is statistically significant or not. Look at this table. And similar to the t-distribution table, we have another one. Your p-value here is 0.05, the critical value. At degree of freedom 1, it is 3.84. Now, if the calculated value of chi-square is more than this, I mean it was 12, more than this, we're going to the right hand side. So the corresponding p-values would be on this upper side, would also be gradually declining. Sorry. So the corresponding value in the previous one is 12, so it might be here 0.001, it could be, which is much less than 0.05. So the calculated p-value is less than 0.05. This is the inference. That means there is a significant difference between anemia and non-anemia between boys and girls. Okay, in the previous example. So here, boys 21 out of 115, 51 out of 112. It seems to be much larger. All the percentage is not given, it is done in the absolute number for the calculation of the chi-square test. Okay. So this is now proved by the test of significance. So we refute the null hypothesis. We say that alternate hypothesis is correct and the prevalence of anemia is more among the girls as compared to boys. This is how you interpret it. Okay. So the inference for 1 degree of freedom, the critical value of chi-square is this much, and your p-value at 0.01 level is 6.64. The calculated value is more than the critical value at 1 level, 1% significant hypothesis, p less than 0.01, which is less than 0.05. Okay. So the problem is interpreted as null hypothesis rejected and concluded that anemia status in rural children is associated with gender. Okay. And more common among the girls as compared to the boys. Another way of doing chi-square test when it is more than 2 rows and 2 columns. Please try to understand this. For contingency tables, 2 rows, 3 columns, 2 rows, 4 columns, like that. 3 rows, 4 columns, any of this. the formula is given by this. Chi-square value is given by summation of, in bracket, observed minus expected whole square divided by expected. So that means you expect that there will be different cells, and for each of the cell, you calculate the difference between observed and expected value. Okay, observed minus expected square. How to do that? See this example in the only 2 by 2 table. Now, smoking is present absent, and based on the smoking status, based prevalence of myocardial infarction. Now, 100 smokers and 100 non-smokers. Here it is given written X and Y, and A is the prevalence of MI among those who are smoker, and C is MI present among those non-smoker also. So that means 70 out of 100 and 10 out of, these are the observed values. Now, how to calculate the expected value? Now, presuming that there is null hypothesis, there is no significant difference between the smokers and the non-smokers. I club them together. So that means the final one, how much? 80. 80 MI is present in the population out of 200. So this is the expectation. That means 80 out of 200 is your 40%. 80 divided by 200 multiplied by 100. So that is your 40%. Okay. So based on that, you calculate your expected value. So that means the observed value, how much the expected value based on this total. 80 divided by 200. You multiply it by 100. These are expected values. Okay. So that will be like 40. And here again it is 120. So 120 out of 200 multiplied by 100, that will be 60. So like that, you calculate for this. So you have observed also and expected value also. Similarly, so you can calculate this 0.4 into 140 expected like that. So then you calculate all the different values and add up together. Okay. I'm not going to this job. You can look at this. Observed minus expected for the first cell. Observed value is 70. Expected is 40. Here it is written on the left hand side. Squared divided by 40 is the expected value. Then summation with the second cell. Observed is 30. Expected is 60. Like that. Divided by expected. Like that. You calculate for this also, and ultimately you get 75 is the chi-square value for degree of freedom 1. All right. So in that example, I told you that in degree of freedom 1, the chi-square value, if it is more than 3.84, so this 75 is much more than 3.84. So in that case, your corresponding p-value will be less than 0.05. So I can say that your null hypothesis is rejected, and you can say that myocardial infarction is more prevalent among smokers as compared to non-smokers. Okay, so this is all about your test of significance. Thank you all. It is a bit tough to continue for such a long time, but because of the prevailing condition, we have to shorten everything in this session only. But we'll be again giving you the sums. The practicals will be done by our senior residents, and in the practical sessions, whenever you come to the department in rotation, now the first rotation is the first group is here within the department. The second group will come subsequently. The third will also subsequently. But try to come reading these different aspects so that it will be easier for you for the practical classes during the statistical test. Okay, so thank you all once again, and wish you all a happy learning. Although it is difficult to say for the biostatistics class, unless you do it again and again, it will be difficult for you to learn. But then, once I've given you the theoretical framework, it will be easier, little bit easier for you. So go through your books, books on the biostatistics, and also books from your park also, where t-test is not given, but still you can go ahead with the chi-square test. But then we'll again brief you in details about the t-test. So thank you all. I'm not taking any answers. I'm not taking any questions from you, but then we'll be doing this during the practical sessions.